Welcome to The Explainer. Today, we are diving into something absolutely wild. We're decoding a truly fascinating, completely futuristic engineering protocol called Hempoxies 71. I want you to imagine taking one of the most structurally demanding materials on Earth, high-performance carbon composite, and just totally reimagining it from the ground up using bio-based, recyclable chemistry. Well, that is exactly the audacious goal of the scientific manual we're breaking down today. It's a dense read, and it's highly technical, but I promise you, by the time we finish this explainer, you're going to understand the exact mechanics of how this sustainable supermaterial is designed to actually work.
Okay, let's dive into our roadmap for today. We're covering 6 main parts. 1. The blueprint. 2. The bio-based ingredients. 3. Mixing the high-tech recipe. 4. Synergy, how it works. 5. Safety and reality checks. And 6. Recycling the future. Let's get right into it.
So, to really appreciate this document, we have to start with a massive real-world problem. Traditional carbon fiber composites are incredibly strong and lightweight, right? That's exactly why they're used in everything from airplanes to wind turbines. But here's the catch. They are notoriously difficult and often literally impossible to recycle. The vast majority just end up sitting in landfills. So the core ambition of the Hempoxies 71 protocol asks this radical question. What if we could build these high-performance, resilient materials almost entirely out of hemp and somehow make them completely recyclable?
Now, before we get lost in the chemistry weeds, we need to establish exactly what it is we are looking at. This is a technology readiness level 1 to 2 design hypothesis. So Hempoxies 71 isn't a finished commercial product that you can just go buy today. No, it's a forward-looking research initiative. Every single numerical property we discuss is a projected design target or literature-derived estimate. It's offering up falsifiable targets to guide really rigorous experimental work. Basically, it's a transparent, hallucination-free roadmap for materials scientists to follow and validate.
All right, moving to Section 1, the Hempoxies 71 Blueprint. The absolute ultimate goal of this protocol is to create a multi-scale composite that maximizes stiffness, strength, and electrical connectivity. But here's the kicker. It aims to do all of that while hitting a massive target of being at least 88% bio-derived by weight. By using a hemp seed oil glycidyl ester epoxy and combining that with a bio-based furan-reactive diluent, these designers are pushing the absolute limits of just how much renewable biomass you can pack into an industrial-grade composite.
But the real secret to this blueprint? It's a concept called a Vitamer. See, traditional plastics are usually either thermosets, which are super strong but will just burn if you heat them, or thermoplastics, which you can melt down, but they aren't nearly as structurally sound. A Vitamer is kind of the holy grail of plastics. It's strong like a thermoset, but thanks to a really complex bit of chemistry called transesterification, its internal bonds can dynamically exchange when they're exposed to specific heat, which means you can reshape it, you can weld it, and you can totally recycle it without losing its high-performance properties. It's a total game changer.
Okay, on to Section 2, the bio-based ingredients.
Let's break down this incredibly complex recipe. If we look at a 100-gram composite basis, over half the weight, 55% to be exact, is the primary structural reinforcement, which is hemp short carbon fiber. That massive loading is what gives the bulk material its strength. To bind all that together, it uses 19.5% Zilla hempoxy resin and 8.7% bio-based diacid as the crosslinker, which is what creates that magic Vitamer matrix. They also throw in a specific FGO diluent at just under 5%. That's to control the viscosity so that all this fiber can actually be wetted out and mixed properly without turning into a clumpy mess.
Now, what's really interesting about this slide is the inclusion of 10% acid-functionalized hemp biochar. In your standard composites, once a crack starts, it can spread rapidly and lead to catastrophic failure. But the literature cited in this protocol shows that at roughly a 10% loading, this highly porous pyroleic biochar acts as a toughening agent. Think of it like microscopic rebar sitting right there between the fibers. It physically blunts and deflects cracks, completely converting a normally brittle material into something with quasi-ductile toughness.
And to round out the ingredients, we have just 1.5% hemp carbon nanosheets, which the framework provisionally calls mitlinite. Even at this tiny percentage, these 2D sheets are absolutely critical. Because they sit right above the electrical percolation threshold, they literally create conductive bridges all throughout the resin. So they aren't just there to add strength, they are fundamentally transforming the entire composite by adding through-thickness electrical connectivity.
Moving into Section 3, mixing the high-tech recipe. The document actually provides a highly specific standard operating procedure for mixing this stuff. It reads a lot like a futuristic high-stakes cooking show where your shear speeds and your vacuum pressures matter immensely. First up, the nanosheets are let down into the resin under vacuum. Gotta prevent those air bubbles. Next, you incorporate the biochar using a massive 2,000 RPM high shear mix. Then comes the really critical step, the fiber wet out. That 55% load of carbon fiber has to be added super slowly in 4 distinct increments over 40 minutes, at much lower speeds so you don't snap the fibers. Finally, the curing agent goes in at exactly 40 degrees Celsius before the whole mixture heads into a multi-stage thermal cure cycle.
Next up, Section 4, Synergy, and how this all works together.
And this brilliantly illustrates how every single ingredient has a multifunctional purpose. This drives the 4 core synergy hypotheses of the whole design. First, you've got hierarchical stress transfer. The nanosheets actually smooth out the stress jump between those super rigid carbon fibers and the softer resin. Second, as we saw earlier, the biochar is in there blunting and deflecting cracks. Third, the nanosheets in the biochar team up with the primary fibers to create a highly effective electrical network. And fourth, the specific Vitromer matrix allows for that amazing dynamic reprocessability.
Which brings us to Section 5, Safety and Reality Checks. So the protocol lays out what we call a projected performance envelope. It's targeting a flexural strength of over 450 megapascals and a flexural modulus of over 35 gigapascals. But the author firmly and repeatedly reminds us these are unvalidated aligned fiber aspirations. If the short fibers end up laid out in a random planar orientation, which frankly is highly likely if you're using a book molding process, the stiffness is going to be a fraction of these targets.
And staying on that point, the document leans super heavily into a fiber property reality check. See, earlier drafts of this work optimistically quoted a hemp fiber modulus of around 150 gigapascals, but this current version corrects the record. It notes that real-world lignocellulosic carbon fiber realistically tops out at a modulus of 46 to 100 gigapascals today. It explicitly tells researchers to design with a much more conservative 60 to 80 gigapascal expectation. And honestly, this level of self-correction is exactly what makes a TRL 1-2 document like this so trustworthy.
Now keep in mind, this theoretical blueprint is also deeply grounded in some pretty harsh real-world chemistry. There are mandatory safety precautions outlined here that were absent from earlier drafts. It warns that anhydride curing agents are respiratory sensitizers, the nitric acid used to functionalize the biochar can actually evolve highly toxic NOx gas, and that superfine carbon dust, yeah, that's a combustible hazard requiring strict HEPA extraction. It's a pretty stark reminder that just because a material is green and bio-based, the chemical engineering required to synthesize it is intense and absolutely demands serious laboratory safety.
Finally, Section 6, Recycling the Future.
Let's move to the end-of-life plan and see how this builds directly on that Vitromer chemistry we talked about earlier. It is incredibly versatile. Because it's a Vitromer, you can just grind the composite down to 5mm pieces, apply heat between 180 and 200 degrees Celsius, and you can literally press it into a brand new shape as the internal bonds just flow and reconsolidate. You can even weld broken pieces back together using optional Diels-Alder-Furan chemistry. Or if you want total chemical recovery, you can just submerge the whole thing in an amine solution. That dissolves the matrix and lets you recover the raw carbon fibers entirely. It's brilliant.
So what does this all mean? Well, Hempoxy 71 provides us with an incredibly detailed, falsifiable, and rigorously caveated roadmap for a sustainable, fully recyclable supermaterial. It lays out the exact validation steps needed to move from a design hypothesis to physical reality. The chemistry definitely works on paper, but the real test is going to be in the lab. So the question we're left with now is, how quickly can materials scientists execute this roadmap, validate these ambitious targets, and actually transition this brilliant scientific blueprint from the lab bench into the real world? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.